I saw tigers, now I understand.
Hey, all you cool cats and kittens. It's time to do some physics. On the agenda today is the real introduction to thermodynamics. We did topic 3 earlier last year, this year, I don't know. But while that was thermodynamics and some of the basics, and we did talk about some gases in topic 3, a lot of the more typical concepts that you see in a college thermodynamics class are hidden here in option B. All of section B2.1 right here, this is the entire B2.1 section from SOCOS. I just copied and pasted it. And we've already seen this formula when we talked about the energy content of an ideal gas. And you might remember that this first equation right here was a really famous result derived by Maxwell Boltzmann. And it relates the average kinetic energy of the particles in a gas. It relates that, which is sort of a microscopic concept, to a macroscopic concept of the entire gas, which is temperature, which was kind of a big deal at the time. It was one of the first very successful statistical mechanics equations. And a statistical mechanics is a way of describing physical concepts in terms of statistics and in many numbers of particles. But because there's so many particles, you can't really keep track of what each one is doing, so instead you keep track of various statistics regarding them. And this is just a simple example, but average kinetic energy turns out to have a pretty big meaning. It relates the root mean square velocity of the particles to the temperature of the gas, and it kind of gives our definition of temperature. Temperature is a measure of the average kinetic energy of the particles. For this section, you really just need to remember that U is the variable we're going to use for internal energy. That's how much energy the gas has within it. If you add up all the kinetic energy of the particles and all the potential energies between the particles, that is internal energy. So internal energy is kinetic energy of the particles plus potential energy of the particles. Except for an ideal gas, there's never any potential energy between the particles, because one of the assumptions in making an ideal gas is that there are no forces, there's no electric or gravitational force between the particles when they're not in contact with each other. That's one of the things that begins to break down when a gas gets really dense or begins to not be described well by the ideal gas law. So if there's n particles, then n times the average kinetic energy is the total internal energy, as long as there's no potential energy, which there's not for an ideal gas. So the average kinetic energy is 3/2 kT. N times 3/2 kT, that's what this equation is. That's the total internal energy of the gas. You can rewrite that in different ways. If you use the ideal gas law, you could say that it's also 3/2 times P times V, or 3/2 times nRT. All of these are equivalent. A change in internal energy comes from, well, there's different ways you could change the internal energy. If you're looking at this equation, you could change the number of moles present, or you could change the temperature. Those two things would change the internal energy. If you're looking at this one, you could change the pressure or the volume, and those things would change the internal energy. A very useful equation is this one, however, that change in internal energy is equal to 3/2 times N times R times delta T. So very quickly here you can see that if a process doesn't have a change in temperature, then there won't be a change in internal energy. And that's very useful when you go to work different problems. All right, moving. Just to remind you also, Boltzmann's constant, K, is 1.38 times 10 to the negative 23 joules per Kelvin. Also, if you forgot, lowercase n is moles, uppercase n is number of particles. 2.2, which is also a pretty simple section, has to do with systems and the way, really vocabulary for describing things. Remember, a system is just an imaginary boundary kind of that you draw around whatever it is that you're trying to model. So let's say I'm trying to model a hydrogen gas. If I draw a boundary around the hydrogen gas, now I can say that things are in the system or things are outside the system. These are the surroundings. That's the system. And we can say that particles can flow across the boundary sometimes. If particles can flow, that's called open. That means mass transfer can happen. Closed means no mass transfer can happen. Isolated means that no energy exchange happens. And there's not really a word for systems where energy does flow across the boundaries, because that's most systems. Okay, the only other thing in this section, 2.2, is a discussion of the state of a thermodynamic system and processes. So a thermodynamic state is when enough variables are set or known that all of the other variables that could describe the system must have some value. So state variables are things like temperature, pressure, number of atoms, volume, these are all, these are basically the things that show up in the ideal gas law. There are more that you learn eventually if you keep going in thermodynamics, but these are the good ones that we need. When you have 3 of these defined, the 4th one is set. Just think about the ideal gas law. PV equals NKT. If 3 of these are set and K is a constant, then the 4th one can only be one thing. It can't be anything else. So knowing 3 is enough to know the state of the thermodynamic system. It means that if you wanted to, you could figure out all of the other state variables that exist. So that's a state. A thermodynamic state is when you know all of the thermodynamic state variables, or you know enough that the other ones have to be some set value. When a state changes when any of the state variables change. So like if temperature changes just a little bit, that's a completely new state. All of the state variables probably are adjusted in addition to temperature. So it's a completely different state. So a process, or a thermodynamic process, is when a state changes. Or the process itself is going from one state to another. And there's different kinds of process. There's different ways you could change states. Some of the simple, what you typically do is describe some simple ways that a state could change, and then any real, more complicated process is probably made up of those simple changes. So things that are simple are like constant pressure. The state changes from one state to another, but the pressure doesn't change. Or constant temperature. Or constant volume. or no heat transfer happens. These are, I'm not just randomly writing these down, these are 4 of the most commonly learned simple thermodynamic processes. And they have special names just because we want to be complicated. Just because it is the goal of every engineering department to make as many people fail as possible when they take thermodynamics. Just kidding, that's not the goal. But it is often, the class thermodynamics in an engineering curriculum is often thought of as the weed out class. For those people who made it through some maths and some physics, they're like, yeah, fine, but take this. And this class is often where people are like, oh, I don't really want to do this. Like for pre-med majors, pre-med's not really a major, but for people who want to go to med school, that class usually is organic chemistry. When you get to it and you're like, oh, okay, I don't want to do this. The common names for these are iso, meaning same, baric, meaning pressure, iso thermal, which is a little misleading. You would kind of think that the last one would be called that. Constant pressure, everyone else typically calls this isochoric, but SOCOS and or IB Physics likes to call it isovolumetric. If you take thermodynamics in college, people are going to call it isochoric. It's pretty easy, though, if you read the word isovolumetric to figure out what thing is staying constant. No heat transfer is called adiabatic. Adiabatic. And it's a weird one. The results of an adiabatic process are often non-intuitive because we don't really experience many adiabatic processes. When we talk about it more, I'll give you some examples, though. So, these are ways that the state could change from one state to another. And we'll see what... There's a very popular way of graphing these called PV diagrams, pressure volume diagrams. We'll see what each of the processes look like on PV diagrams. And the reason that PV diagrams are so useful, you will see in the next section, which is about work done by gases. So I'll leave that surprise for the next section. But in this section, we'll talk about what do the different processes look like on a PV diagram. Isobaric, isochoric. These are the 2 easiest ones to draw because they're literally on the axes. So isobaric is just a horizontal line with the same pressure the whole time. Isochoric is just a vertical line with the same volume the whole time. There's no other way to draw those. If it's isobaric, it has to be a horizontal line on this graph. If it's isochoric, it has to be a vertical line on this graph. However, isothermal is it's not really hard to figure out, but it's not as easy to draw, or at least freehand for sure. Isothermal, you got to kind of think, we've got a graph of pressure and volume, but we want temperature to remain the same. Is there some law that you know that relates pressure and volume and temperature? And usually when we're talking about these things, it's probably better if you just always think about gases. You don't start talking about real thermodynamics of solids and liquids until you basically master the thermodynamics of gases. And that's because gases are a lot easier to describe because of the lack of interactions of the molecules and the particles with each other. In a liquid or a solid, when you've got all the different interactions happening between the molecules, the thermodynamics of that system are a lot more complicated. So it's helpful if you just remember that we're probably talking about gases. So what gas law do you know that relates pressure and volume and temperature? That's right, it's our old friend, PV equals NKT. So if temperature is constant, then that means pressure times volume has to be constant. If pressure is the y value, that means there's some constant divided by volume. That looks like y equals 1 over x. You know, my y variable is p, my x variable is v, and all this stuff on top is a constant. So that looks like this, you know, to some extent. It's a 1 over x looking graph like this. Isothermal. And the last one, adiabatic. Adiabatic looks a whole lot like isothermal. It's just that the line, steeper is not quite the right description, but it's what people say a lot of times. I like to say that adiabatic lines always involve a larger delta P for the same delta V. So actually it depends on, I drew 2 arrows a while ago. That's completely wrong. You'll never see a process that's got 2 arrows. A process has to have a direction. It's going from here to there. You could reverse it and go the other way, but then the arrow would be going the other way. Adiabatics always have a larger change in pressure for the same change in volume when compared to isothermal processes. So if you remember that, and I show you a graph of 2 curves, and I say one of them is isothermal and one of them is adiabatic, you should be able to figure out which one is which. Like, let's do that right now. Here's a PV diagram. Here, I'm going to draw it between these 2. Let's say it's compression, so it's from a smaller volume. No, it's from a larger volume to a smaller volume. One of them goes there, one of them goes there. So we've got 2 curvy lines. One goes there, one goes there. Which one? One of them's isothermal, one of them's adiabatic. You tell me which one is which. If you said the top one is adiabatic, congratulations, you got it right. If you said the bottom one was isothermal, congratulations. The reason I know that has to be right is because they have the same change in volume. The adiabatic one's got to have a larger change in pressure. It looks a little different if you go it doesn't really look that different. If you start at the same volume and you end at 2 different volumes. Now, this one's got to be the adiabatic one because it has a larger, from here to here, larger change in pressure than from here to here. So I told you the reason why the isothermal line looks like this. I haven't yet told you why the adiabatic line looks like this. That's something after we learn the first law of thermodynamics, which is coming up in the next couple of sections. But now we need to talk about the work done by a gas. So a gas can do work if you arrange the situation so that it is trapped somewhere, and the classic example that every textbook uses is a cylinder and a piston. You may have heard of pistons and cylinders in reference to car engines. That's because car engines have cylinders and pistons in them. And what a typical cylinder and piston do is there is as tight of a seal as there possibly can be at the edge between. So the piston, this is the piston, it can move up and down. The cylinder is literally just a cylinder that is closed on the bottom, and I'm not drawing it in 3 dimensions, but it's a cylinder. The piston is a circle, and the piston goes down and up and down and up and down and up and down and up. And it's in an actual car, there's a crankshaft that is rotating. And through clever mechanical engineering magic, the piston is connected via some arms that cause this crankshaft to rotate whenever this moves up and down. And in a real car engine, there's usually more than one, not usually, there's always more than one cylinder. Some cars are V4s, which means there's 4 cylinders. Some cars are V6s, which means there's 6 cylinders. I'm kind of going off on a tangent on cars here, but it's where most people have heard of pistons and cylinders. If you look at the engine of a typical car, the pistons or the cylinders and the pistons are arranged in a V pattern, and the pistons move in and out like this, move in and out like this, and the crankshaft is running down the middle somewhere right here, rotating, and there are arms that cause that piston to rotate just right whenever cause that crankshaft to rotate just right whenever the piston goes up and down. And if you have 4 or 6 or 8, or in crazy cars, 12 pistons, they have to be timed. Ideally, you want one of those pistons always to be applying a torque to the crankshaft so that it always is experiencing a torque to cause it to keep rotating. And if you time them cleverly, then each of their power strokes, which is when they're pushing on the crankshaft, each of their power strokes happens at a different time, and they're sequential. And so the one problem that can happen in some engines is that the timing of the pistons gets off, and that's not good for the crankshaft, because then you've got competing torques from different pistons that aren't happening at the same time. You could literally shear the crankshaft and completely crack it. Modern cars don't do that as much anymore. Anyway, enough about cars. That's the biggest practical application of a piston and a cylinder, and engines of all kinds. It's pretty much the whole reason the piston and the cylinder was invented in the first place. But you have a gas in the middle in here, and in a real car, that gas is made up of gasoline vapor and an air mixture, a fuel and air mixture. And there's a spark plug somewhere, and on the correct part of the cycle, the spark plug goes off and ignites the mixture. And that's when the piston is all the way down at the bottom. There's ignition, it happens, boom, fire, explosion, and it pushes the piston back up. That's the power stroke. And then an exhaust valve opens somewhere, and the piston comes back down and pushes everything out. And almost at the same time, that exhaust valve closes, some new fuel and air mixture is squirted in, and then it starts over. That's a very rough summary of the cycle of an internal combustion engine. We normally would never ask you anything about internal combustion engines, really. But pistons and cylinders definitely show up, because they are how you can explain that a gas can do work. So here's a gas, it's in here, it's trapped. Let's say that the piston is a little bit lower down, and so here's the piston, and let's say there's a block on top that has a mass M. If the piston is stationary and it's not moving up or down, then what's holding the piston and the block up? It's the gas colliding with the walls of the cylinder and colliding with the piston, exerting a force. Well, gas holds piston plus mass up with a force. What force is that? Usually you know or can measure the pressure of a gas more easily than forces exerted by the gas. So if there's a pressure gauge in here somewhere, we could know the pressure that the gas has. Well, pressure is force per area that gas can exert. So if we knew that the cylinder had a surface area Oh, hold on. If we knew that this piston had a surface area, it's a circle, surface area is A. Then we could actually calculate the force that the gas is exerting on that piston. It would just be pressure times area. All right, we'll think way back to static equilibrium problems. That mass is being pulled down by gravity. It's being pushed up by pressure times area. And I said at the start, it's not moving up or down. So that means the sum of the forces has to be equal to zero because there's no acceleration. And if up is positive, that means pressure times area minus m times g equals 0. That means pressure times area equals, wait. The next thing we can do with this is say, what if very slowly we add some energy to the gas? Maybe we're heating it up with a flame. We're adding some energy to the gas in some way. If you do that, then the molecules of the gas have more kinetic energy. Therefore, when they collide with the walls, they collide with more momentum, and therefore they can exert more force on the piston. So if it was in equilibrium and then we started adding some energy, and then the gas starts exerting more force on the piston, what's the piston going to do? It's going to go up. Okay, so here's the wavy hands part of this proof. We're going to say that it moves up in a state that's called quasi-equilibrium. It's kind of fake. Piston moves very slowly, so that it's basically, if you looked at it at any moment in time, you couldn't even tell it was moving. It's basically still in equilibrium. That basically is air quotes. But it does have a net force upwards. It is moving upwards very slowly. It's a good approximation, though. We can say that it doesn't have any extra kinetic energy, and it's moving so slowly that let's just kind of pretend like it's still in equilibrium. It's very hand-wavy. It's very physics-like to do this kind of thing in a proof. It's certainly an approximation. It moves up slowly. If it moves up slowly, then really the only energy consideration we have to make is that it gained potential energy. You know, it was at this height, let's say it ends up here, here it is up here, after it has moved, and it went up by some height h. Well, if it moved this slowly the whole time, then it doesn't really have kinetic energy as an approximation, but it does have more potential energy. How much more potential energy does it have? If it was, let's say it was at 0 potential energy at this initial height, then it gained mgh literally. And it gained that because the gas pushed it upwards. Well, if a thing pushes another thing across some displacement, then what's the name of that process? Work. The gas did work. And work is force times displacement, right? So the work done by the gas has to be equal to the force that the gas exerted times the displacement that it moved the thing. Well, we're saying that it was basically in equilibrium the whole time, even though it slightly wasn't. So if it was basically in equilibrium the whole time, then the force is mg. I know that's kind of absurd, because if it's moving upwards, then it's got a net force upwards, so the force has to be a little bit more than mg. I know. Quasi-equilibrium. It's a very physics-like thing. The displacement is h. So the work done by the gas is m times g times h. But up here, we saw from a free body diagram analysis that m times g can be rewritten as p times a. So let's rewrite it like this. Well, if you look at the geometry involved, what is a times h? Remember, this is a cylinder, and a is the area of the base of the cylinder. It's really the area of the piston, but we're saying the piston goes all the way to the edges. We have created a little volume here, and that volume that we created is a times h. That's how you find the area of a cylinder. So I could rewrite this formula as p times delta v. I could call it v, but I'm going to call it delta v because I know where this is going. Delta v because it moved and there was a change in volume. And the change in volume is the thing that's important, not actually the initial or the final. It's the change that's important. So this is a really famous result in thermodynamics for the work done by a gas. And one thing I forgot to mention was this is really only true if the gas is at a constant pressure. If the pressure is changing the whole time, then this equation doesn't quite work. It's not that thermodynamics can't handle that situation. You would say that the work done during some expansion instead is this. That's like the work done by a spring. You know, the spring force, the force that the spring exerts changes as the displacement changes. Same thing here. If the pressure is changing as the volume changes, then you've got to split it up into tiny intervals and add them all up. That's an integral. And so in college physics, you'll probably see this equation, and it will be more useful than a constant pressure one like over here. But this is the IB one. And knowing how much work a gas does is extremely useful because pretty much all internal combustion engines perform work by a gas expanding. Even in power plants, turbines are powered by steam, which is a gas. And in a way, this equation leads to how you analyze turbines. Obviously, it's not the same because a turbine is not just a volume that's expanding, but analyzing the energy content of a gas is a big deal and has helped society tremendously in generating energy. Here I said on the last page about PV diagrams that you would see why they are convenient and useful. If you think about this equation, or this one really, if you know geometrically what this equation means, when I have a graph, let's say here's an isobaric process, constant pressure process. It goes from state A to state B. Could you represent the work done in moving the gas from state A to state B? Well, it's pressure times change in volume. Okay, well here's two volumes. So this side is the change in volume. This side is the pressure. What do you get if you multiply this side times that side? It's this area under the curve. So, work done by a gas is the area under the curve on a PV diagram. That's basically why PV diagrams are so useful. When you draw cycles, or we're not to cycles yet, but when you draw a process, you can easily graphically see what the work done would be. Okay, the only other wrinkle I can think of for work and PV diagrams is that the sign of the work, you can kind of see, comes from the formula. Pressure is never going to be a negative quantity, but the change in volume could certainly be negative if the gas went from a larger volume to a smaller volume, so that's a compression. If delta V is less than 0, which is a compression, then the work done by the gas is less than 0. If delta V is greater than 0, which is an expansion, then the work done by the gas is greater than 0. So on a diagram, A to B was an expansion. So the entire area under this is positive. But if you go from B, let's say there's an isothermal compression back to here, then that volume change started out here, it ended there, so that's a decrease in volume. So therefore, this entire area under the curve would be negative. And if you wanted to know the total work done and go, if that's point C, find the total work done in going from A to B and then to C, you would add the first rectangular area to this area, which, if it's isothermal, the only way to find that work truly is to use an integral. But what if there's a PV diagram and you have a process that goes from A down to B like this, and then it drops straight down, let's say, to C, and then it goes horizontally back to D, and then it goes straight up back to A, and it starts over. This is called a cycle, or a thermodynamic cycle. It's when the state of a thermodynamic system goes through some changes, but then ends up back where it started. Or the state repeats in a cyclical manner. And you might notice that there's an area that's enclosed here. Well, if you think about the work done during each of these, so work done from A to B, work done from B to C, work done from C to D, work done from D to A. Two of these are pretty trivial, like B to C. What is the area under the curve from B to C? Well, we could find pressures. This is a pressure volume graph. We could find the pressure at B. We could find the pressure at C. So we now have those two numbers, but this volume is the same for both of them. So delta V BC is 0. So if there's no change in volume, then the work from B to C is 0. There's no area under the curve there. Same reasoning for D to A. There is no area under the curve. And those processes are isochoric. Isochoric processes can't perform work because the volume's not changing. The volume of the gas is not changing. But A to B definitely has a change in volume, and it has two different pressures. So we couldn't really calculate with our handy formula right here. We couldn't calculate the work done from A to B unless we used an integral, which IB physics does not do. But you could represent it graphically. It's just all of the area under the curve, including going down here. And area under curve, let's say. Same thing from C to D, there is a work done, but the volume is decreasing, so that's a compression. So that is this little chunk at the bottom, or rectangle, right here, that's all negative. So if you wanted to find the net work done during this cycle, you would add up all of the individual works for each process of the cycle. So that would be A work done from A to B plus work done from B to C plus this plus this. These two are 0, and so you would end up with the area inside the cycle. Because if that part is subtracted from the work done during A to B, then you're left with just this area in the middle. And that's true for all thermodynamic cycles. You can find their work, like the net work performed by that cycle, by finding the area that they enclose. And if you have a good engine, then that area is large. If you have a bad engine, that area is small. If that area is negative, then you don't have an engine. You have something that you have to give energy.